Now what I'd like to do is move into multiplication of n-tuples, right? And you're going to find out that it's no different than what we've done just now, and I think you're going to learn something from what you, or I should say, tie something together from what we have learned a long time ago in your studies of vectors, all right? So remember, put this on the back burner for a split second, the idea of matrix multiplication, all right? But I want you to think back to the concept of a vector. You probably, watching this lesson, the series of lessons in linear algebra, have taken a physics class at some point, or maybe a trigonometry class, but at some point you've probably been introduced to the concept of a vector. A vector isn't like an arrow in space. It has a length, we call it a magnitude, right? And it has a direction, so it's pointing in some specific direction. So an example of a vector would be like force. I push with so many newtons or so many pounds of force, and I'm pushing in a direction, a specific direction. This direction is different than this one. So this vector is different than this one, even if the amount I'm pushing is the same. But if I'm pointing a different way, it's a different vector. All right? So in physics, or trig, or whatever class you've studied in the past, we usually write a vector with a bar on top, right? And if you remember, we might write a vector something like this: 3i hat plus 1j hat plus 2k hat. Right? And these numbers are the components of the vector in x, y, and z, right? So the I hat means x direction, the j hat means y direction, the k hat means the z direction. The numbers in front of the coefficients are the weightings of those different directions. So this whole concept of magnitude and direction is all wrapped up in this information on the board, all right? We can also define another vector. We can define as many vectors as we want, but in this case, let's call it vector B. And let's say that it had 2i plus 2j plus 1k. You might be wondering, why am I spending all this time talking about vectors? Isn't this a class on matrices? Well, what you're going to find, and I'm going to kind of spill the beans now, I'll come back to it, I'll circle back as we go through this lesson. Vectors and linear algebra go hand in hand like peanut butter and jelly. All right, and that's one reason why linear algebra is one of the core classes that you'll take if you're an engineering student, or if you're a science student, or if you're a math student. Because vectors are used everywhere in almost every problem that you're going to solve, from circuit analysis to force to differential equations. I mean, your vectors are going to be everywhere. And when you really think about it, just kind of use your imagination with me. We know that this number 3 corresponds to the x direction. And we know that this number 1 corresponds to the y direction. That's what this j thing means. And we know that 2 corresponds to the z direction. But because we know that here we have x, y, and z, if we know we're always talking about x, y, and z space, then really the only important information on the board is the numbers, right? If I already tell you, hey, we're working in x, y, z three-dimensional space, and if I give you 3 numbers, and the numbers I give you are 3, 1, and 2. The way we write it out in its full glory is how we've written it here, and that's how you've written it in all your physics classes and trig classes and things before. But really, the I, J, and K are really not that important, because we know that the first number always goes with X, the second number always goes with Y, and the third number always goes with Z, right? So really, remember we talked about the concept of an n-tuple earlier, and we said it's just an ordering of like 3 numbers or 4 numbers or 6 numbers or whatever. Well, really a vector is an n-tuple with 3 numbers, right? The components of the vector are really the important information. And we represent them as n-tuples or as matrices or column matrices whenever we do our manipulations with vectors. And that's one reason why vectors and matrices kind of go hand in hand. Vectors and linear algebra go hand in hand. So let me kind of keep going a little bit here. This is how we write 2 vectors down in terms of their full-blown physics sort of notation that you would see. Now, if you remember, somewhere in physics, you learned about something called the dot product, A dot B, right? And I'm not going to get into the theory of what A dot B means right now. It's not critically important for what we're actually going to study here. But for those of you that are remembering, it's used in the definition of work, force dotted with distance. It's used in the definition of lots of things. Basically, you're taking vector A, projecting it in the direction of vector B, and you're multiplying those lengths together. That's what the dot product's doing. It's chopping down one vector in the direction of the other vector, and then you're multiplying what you have there. But the way you actually calculate it is you look at the 2 vectors and you look at their x components and you multiply them together. 3 times 2 in this case. Then you look at their next components, 1 times 2, and multiply those together, and you add it to what you had previously. And then you add, finally, the z components together, multiplied together, 2 times 1. All right, so we have a multiplication going on, a multiplication going on, a multiplication going on, and then we're adding everything together. That's how we arrive at the dot product, right? And in this case, 3 times 2 is 6, plus 2, and that's going to give us a 10. And so the dot product returns a number. So what we get is a dot b is 10. So it returns a product. So because it returns a scalar, because it returns a number, a scalar, it's also called, I'll say dot product, also called scalar product. So in your book, whatever you're studying, eventually it'll probably talk about scalar product of two vectors. That's just a dot product. They call it a scalar product because you get a number as an answer. The one thing I want to call your attention to real quick, this dot product between two vectors. Okay, notice whenever we actually calculate it, we don't have any x, y's, or z's running around anywhere there. We just notice that we're taking the x components, multiplying them together, the y components, multiplying them together, z components, multiplying them together, and we add the results. So we've got multiplication going on, but then we got addition. Now look at some similarities here. Notice how we multiplied these matrices. We did multiplication of elements, but then we had addition. Multiplication of elements, then we had addition. I'm drawing a parallel because ultimately this dot product is basically matrix multiplication. That's what it is. You're not really taught that in physics. You're taught, hey, calculate the dot product. This is what you do. X components multiply, Y components multiply, Z components multiply, add them up, and you get a number that we call the scalar product of the dot product. Now I'm going to show you that this thing that you've done in physics or in trig or whatever class you've calculated the dot product before really is just matrix multiplication. And following the same rules that we've already talked about for matrix multiplication. And to show you that, let me show you the following thing. All right, notice that this vector A has a bar, lowercase a with a bar, lowercase b with a bar. All right, so if I wanted to represent vector A in terms of its kind of matrix representation, I could call it big A. And I'm going to represent it as a column matrix 3, 1, 2. In vector B, I'm going to capitalize it. I'm sorry, matrix B. I'm going to capitalize it, and I'm going to put square brackets, and I'm going to put those components down a column, 2, 2, 1. I think I need to stop for a second and make sure that you're comfortable realizing that this representation of B, being 2, 2, 2, oriented like a column, and this representation of vector A, 3, 1, 2, oriented as numbers in a column, are exactly equivalent to one another. Whenever I see something written like this, I know I have 3 in the x direction, 1 in the y direction, 2 in the z direction. Whenever I see this, I know I have 3 in the x direction, 1 in the y direction, 2 in the z direction. I know that because I know that I'm working in a rectangular three-dimensional system. So the first number goes with x, second number with y, third number with z. All that's really relevant are the numbers. Same thing with vector B. All that's really relevant is a number. And further notice that this column of numbers is what we called an n-tuple before. So the terms n-tuple and vector are kind of analogous to one another. They're basically the same thing. They're just definitions, different ways to say the same sort of thing. All right. Now obviously I cannot multiply A times B as they sit because if I'm going to multiply matrix times a matrix, I need to be able to go over and down. So I can't multiply them as they sit. Right? But what I can do is I can take the transpose of matrix A and I can then dot it or multiply it by vector B or n-tuple B or matrix B, whatever word you want to use. So if I transpose this, what I'm going to get is 3, 1, 2. I just take the single column, turn it into a row. That's the transpose. And then I'm going to multiply it by this column 2, 2, 1. Now this is a perfectly constructed way over and down to multiply these two matrices together. Notice the number of columns here matches the number of rows here. So whenever I get this guy, it'll be 3 times 2, which will be 6. It'll be 1 times 2, which is 2. It'll be 2 times 1, which is also 2. And so when I do this guy, I'm going to get 10. All right? So you might ask, why am I going through all this trouble? When I'm trying to draw your attention to, and what your book usually tries to draw your attention to, whatever book you're using, is first you need to learn the concept of matrix multiplication. And that's what we did before. And then you understand this concept of an n-tuple, which is just a listing of numbers. And then they kind of come back to vectors, which is stuff that you learned way before. And I know my mind was kind of blown when I started representing vectors as matrices because it just didn't make a lot of sense until I realized that the X, Y, and Z, the labels that we give, or the I, J, K labels, they're really superfluous. They don't really, you don't really need to write them down all the time if you always know you're operating in a three-dimensional rectangular system. Only the numbers are really relevant. And matrices are just a collection of numbers. So basically we can write vectors as a collection of numbers as long as we know that it's x, y, z. And when we write these n-tuples or these vectors, we typically write them as column vectors or column matrices, which is how we had them written here. Now if I want to multiply them together, then I need to turn one of them on its side. So I write this as a transpose, I put it on its side, and then I can multiply there. And so what I'm trying to say, the big giant punchline of the day, is that the scalar product or the dot product that you learned way back in physics as defined as we looked at components multiplication like that is really just matrix multiplication going over and down. That's all I'm really trying to say, right? In the physics world, when you're learning physics 1 or whatever in your first real physics course or engineering course when you're learning about vectors, you don't really need to represent them as matrices because it gets in the way a little bit. That notation gets in the way. You want to write things like this up here because x, y, z, carrying it along is not a real burden. But when you get into linear algebra and you start talking about vectors, and much, much later on, we're going to talk about vector spaces and different ways to manipulate and transform vectors from one space to another, then you're going to really want to represent vectors as basically as what they are, which are n-tuples, which are just collection of numbers, collection of components along x, y, z in this case. All right. So basically the over and down multiplication of two vectors is exactly the same as the dot product thing that you learned a long time ago. So the dot product is basically matrix multiplication. That's all we're really trying to say. So in the general sense, whenever you have vector A dotted with vector V like this, we have A sub 1, V sub 1 plus A sub 2, V sub 2 plus A sub 3, V sub 3. We're multiplying the components of x and y and z and we're adding them together. It's exactly the same as doing over and down the way we've defined it like that. Okay? And just to round it out, I'd like to quickly do a couple of quick examples just to tie it together. So if I had vector u, and I defined it as 1, 3, negative 1, and vector v, which is negative 1, 4, 2. These are n-tuples, just collection of numbers with commas, and I want to dot them together. The way that I would typically do it in a physics class is I would say u dot v, and I would just look and say, okay, the x components multiplied together would be 1 times negative 1. The y components multiplied together would be 3 times 4. The z components multiplied together would be negative 1 times 2, right? Because this is x, y, z, x, y, z. Normally when you write it in a vector form, you have your I component, your K component, or your J component, and your K component. But within tuples, you don't really have to carry all that stuff around. We know that it means X, Y, Z when you have a triplet like that, all right? And so when we dot them together, we look at the first guy's multiplied, second guy's multiplied, third guy's multiplied, and what we get as a result is negative 1 plus 12 minus 2, all right? And then when we get that, we end up getting the number 9 because it's 12 minus 3 gives us 9. So that is the scalar product or the inner product of these two vectors together. And notice also that if I go backwards, I get the same result in this particular case. If I do v dotted with u, right, then I go backwards and go the other direction. I'll go negative 1 times 1 plus going backwards this way, 4 times 3, plus going backwards this way, 2 times negative 1. So what I'll get here is negative 1 plus 12 minus 2, and again I get exactly the same thing, which is 9. So it doesn't matter if I do u dot v, v dot u, you know that from vector analysis back from physics or whatever you studied. If you dot two vectors together, it doesn't really matter the way in which you're doing it. You basically are just doing those components and laying one vector on its side, one vector as a column, and you're just going over and down as you do that multiplication. So I have a couple of things here, one of which I've already said. is that when we have n tuples, so for n tuples, n tuple multiplication, which is just the dot product, multiplication, right? We know that u dot v is equal to v dot u, right? And we also know that u dotted with v plus w is the same as u dot v plus u dot w. So we can kind of take that dot product, if we think of these as vectors, you can take that dot product and dot it in like that, and you get a distributive property. And then finally, when you have a constant involved, k times u dotted with v, so we're multiplying this vector times a constant k, then we're dotting with a vector v, is equal to having a constant u dot v, which is equal to u dot kv. Basically what this is saying is that if I have two vectors u and v, and I multiply by a scalar and then I dot it with the vector, it's the same thing as if I do the dot product first, or if I do this multiplication over here first, or if I do this multiplication here first. It doesn't really matter with a dot product of n tuples. All right? So let me just take a quick second to summarize where we are. I know I covered a lot of material in this section. I wanted to cover it together because matrix multiplication, which we first started this lesson out, is exactly the same as taking the dot product. That's a connection that's important for you to make that usually isn't made until you hit a linear algebra type of course. So some things that you consider separate, you know, like when you first learn about the dot product, it seems like a separate operation than the stuff you're learning about matrices. Here in this class, we're unifying those together, and we're going to be talking about vectors more and more as we go, because vectors, now you should know, are just matrices. We call them n tuples because they're just a single list of numbers. All right, so we have matrix multiplication. It's only defined when the columns of the first matrix is the same as the rows of the second, and you have to go over and down and over and down and over and down to get the different elements of your answer. All right, and then we said that depending on the dimensionality of the matrices you have, you may not be able to multiply them at all, and that just basically goes with what we said a minute ago. But if you can define an AB multiplication, then when you do the reverse BA, you're not always going to get the same answer. In fact, we gave an example where we flipped the order of multiplication, we got something different. All right? And then we gave a few properties that I don't expect you to memorize. Nobody expects you to memorize them. I'm just trying to present them to you for completeness so you can be exposed to them. And then I'm trying to make this connection to vectors, because your linear algebra course is going to get into vectors pretty fast. And I'm trying to remind you that you know how to write vectors in terms of IJK form, and you've already been exposed to the dot product at some point in the past, which you already know how to calculate, and we've done that here. We also call it the scalar product because that operation returns a number, a scalar, right? And then I'm saying, hey, you can represent vector A as an n tuple like this, and vector B as an n tuple like this, which are just matrices, column matrices, because really it's implied, x, y, z, it's implied in your coordinate system that you have. So it's very, very elegant, really, to represent your vector as just three numbers like this. And it's representing where your arrow is pointed in space, basically. So if you're working with a computer, trying to program a computer, you're pretty much going to deal with triplets of numbers when you're dealing with vectors. And that's very easy for a computer to use. You know, three numbers, you can manipulate numbers all day long. That's what computers are good for. And then we said, hey, if we want to multiply these together, we can't really do it as they sit because the dimensionality is wrong. So we have to lay this one on its side, and so we transpose it. And then when we do that, basically we compute the matrix multiplication. We end up getting the same answer for the dot product. So it's kind of implying that multiplying vectors or multiplying n tuples together is just matrix multiplication. And that's the big connection I'm trying to make in this section, is that number one, I want to review you on how matrix multiplication happens, what makes it tick, get a little practice with it. And secondarily, I want to remind you or show you about the dot product and to show you that that's really just also matrix multiplication. So make sure you understand this stuff. I'm going to be touching on this as we go through the course. Quickly, we're going to be getting into more vector terminology, and that is just coming about because of this connection here, because vectors really are matrices, which we call them n tuples because they're just a single list of numbers. That's where we're going. And then we'll get into some more topics that are also critically important. So make sure you understand this, and then follow me on to the next lesson, where we will continue in linear algebra.